Hello there guys, and welcome back to another epic inexorable maths video. In this video we're looking at integration by substitution. This is another incredibly powerful method for integration. So we're going to check out what exactly is in this video and also look at a few examples. There'll be lots of examples coming in the future in separate videos of their own because they're more complicated, but let's get the general premise of it down. So let's just start off with an example. The easiest way to do this is by example, and I'll kind of talk through what we're doing as we go through. So let's consider something like the integral of x multiplied by 1 plus x, the square root. So x times the square root of 1 plus x dx. Okay, let's consider doing this integral. Now, the thing is that this is not a reverse chain rule, and I'll leave the reverse chain rule video link in the description below, but it's not a reverse chain rule. If this was 1 square root of 1 plus x squared, then yes, it would be a reverse chain rule because you'd be multiplying by a multiple of the derivative of the inside of that sort of bracket to the half, if you like to think of the square root in that way. It's not that, so because there's no squared there, so it's not a reverse chain rule. You also can't just integrate it. You can't do that. So the question is, how do we do this thing? Is it even possible? Yes, of course. The easiest way to do this is by doing a substitution. Okay, so what you do is you normally are going to be looking at the thing that makes this a bit difficult. Wouldn't it be nice if that 1 plus x was just one thing? Because if this was like, you know, something times just x to the half, not 1 plus x to the half, if it was just x to the half, it would be nicer. So why don't we say, and we normally use the letter u, why don't we say, just like the chain rule, we use a u for the chain rule. Substitution is kind of linked to the reverse chain rule. You can do reverse chain rule questions using a substitution, but this is kind of separate as well. We're going to say let u equal, and for this specific question, it's going to be 1 plus x, okay? It's going to be 1 plus x. If u is 1 plus x, then we can rewrite this integral as x. Well, if u is 1 plus x, then that means that x must be u minus 1. So instead of x, I'm going to write u minus 1. And instead of 1 plus x, I'm going to write u. So it's u minus 1 times the square of u dx. Okay, this is the integral of then, well, u square rooted is u to the power of a half. So u to the 1, this is a u to the 1, multiplied by u to the half is u to the 3 over 2. And minus 1 multiplied by the square root of u is just minus u to the half dx. But you might say, okay, fine, sure. What we've done so far is we have said, we've got a bit of a tricky integral. X times the square root of 1 plus x. We don't know how to integrate it. Why don't we do a substitution in order to make it easier? That's basically the entire point. Notice how u to the power of 3 over 2 minus u to the half is easier to integrate than what we began with. The only problem though is that we're still integrating with respect to x, because all we've done so far is just replace f with some u's, you know, but dx is not du, so we can't integrate this. If only there were a way to figure out what du is in terms of dx and vice versa, so that we can replace the dx with some sort of du. Well, there's an equation that links x and u together. X equals u minus 1, or u equals 1 plus x. If you differentiate both sides of this with respect to u, then you get dx du equals 1, which means that dx is equal to du, just multiplying both sides by du. Which means that you can actually just replace dx with du in this specific question. It normally won't be like that. Normally it won't be so simple. But in this specific question, yes, it is. So now this is actually just the integral of u to the 3 over 2 minus u to the half, and not dx anymore. Dx and du are the same, so we can write du. And then you just do the integration, all with respect to u. Okay, so u to the 3 over 2 is going to integrate to 2 over 5 u to the 5 over 2. Just this, that's the power rule. Both of these are power rules. Minus, and I think that's going to be 2/3 u to the power of 3 over 2. And you can check this by doing differentiation plus c. Now, if someone ever said to you, hey, what's the integral of x times the square root of 1 plus x? And you said, the answer is 2/5 u to the 5 over 2 minus 2/3 u to the 3 over 2 plus c. They'd say, what on earth are you talking about? I don't know what u is. So what you need to do is replace the definition of u with what it is in terms of x. In this specific question, we said that u is equal to 1 plus x, you can see there. So all we do is we come down here and we can say finally that the integral of x times the square root of 1 plus x, that was the original thing that we began with, dx is equal to 2 over 5, and u is 1 plus x, so 1 plus x to the 5 over 2, minus 2 over 3 u, u again is 1 plus x to 3 over 2, plus c, and that would be the answer. You can factorize this and simplify the answer a little bit, but if we don't look at that, that would just be your answer. That's the answer to that integral. So it looks, oh, it's actually quite a complicated one. Yeah, it is. I suppose it is. But that's how you would do that with substitution. So basically, the gist of it is, we've got a complicated integral. Sometimes you can do a substitution to simplify it. Sometimes you can't, sometimes you can. If you can, have a go. See if you can sort of guess what the substitution is. If you have a square root, the substitution, not always, but tends to be what's inside of the square root. Sometimes it will include the square root, sometimes it will not. You have to be a little bit clever about it. Maybe you have to try multiple things. And then you do the integration in terms of u, which will normally be easier, simpler, an easier integration. And then you just replace the u's again with x's after you've integrated it, which is very cool. Let's have a look at another one. Okay, we've got another question chilling out right here. So this time, we've got x times 3 plus 2x to the 5, and also it's definite integration, which means that there's limits in here. So we're actually kind of trying to find the area beneath this curve in between 1 and 5 on the x-coordinates. So you might say, that kind of adds a bit of complexity to the mix. You're absolutely right, it does, but it's okay, we can still do it. So let's do the normal thing that we do. First of all, we need to identify the substitution. It's normally the thing inside the bracket, it's underneath the square root. So I can say, I'm quite happy to say, let u equal 3 plus 2x. And I'll move my screen so you can see that, just to be really clear. 3 plus 2x is going to be our substitution. Because if this is the case, and by the way, we can also rearrange this for x in a second because there's an x on its own over there. But if this is the case, we can rewrite this integral. I'm going to write for the limit x equals 1, x equals 5, because you'll notice in a second we need to change these limits. So I'm going to remind myself, yeah, these are definitely in terms of x. We're going to change them into u's later, but that's why I'm writing x equals. It's still between 1 and 5, no change there. Okay, so x, well, first of all, we don't know what x is. I'm going to put x there for a second. We don't know what it is. And that's going to be multiplied by, and 3 plus 2x, that's literally u. So it's literally just times u to the power of 5 dx. But let's actually figure out what x is. So if u is 3 plus 2x, then that means that u minus 3 is 2x, meaning that x is going to be u minus 3 over 2. So let's actually replace x with u minus 3 over 2, because that's what it is. The whole point is to get rid of all of the x's, replace them with u's. So this is u minus 3 divided by 2. That's our integral. Okay, we still need to deal with the dx. First of all, you're allowed to factor a common multiple out of any integral that you want. So the whole thing's being multiplied by a half in a way, because you have a u minus 3 divided by 2. I'm going to write this as 1/2 the integral between x equals 1 and x equals 5 of just u minus 3 times u to the power of 5. And that's going to be dx, but I won't write dx just yet because you'll see in a second. But the half, the over 2, has come outside of the integral. You're totally allowed to do that. That's completely fine. Just makes it a bit more simple. Okay, so the dx, let's deal with the dx. We want to know what dx is. So the way that you find dx is however you want, really. I think taking the original equation is nicer. We can find du dx. So it's either going to be dx du or du dx, whichever one you prefer, doesn't matter. And this is going to differentiate to just the number 2, meaning that du is going to be equal to 2 dx, meaning that dx is going to be equal to 1/2 du. So what that means is we can replace dx with 1/2 du. So I'm going to write 1/2 du. That is dx. We've just worked out that literally is what dx is. So I'm going to replace that. So we've then got another half in the mix. I'm going to take that out again, and that's going to become 1/4 now, because the half from the half du is going to come outside. I'm then going to expand this out. U minus 3 to the times u to the 5 is going to be u to the power of 6 minus 3u to the power of 5 du. Okay, so this is our integral so far. So you can see whenever you have brackets, right, the thing that's nice is that the thing that has the power becomes the thing on its own, and the thing on its own becomes this kind of weird binomial sort of thing. Like, you know, you have a u minus 3, but it's okay because it's not raised to a power. Whereas if we scroll right up to the beginning, the binomial is what's raised to the power. You can see that here. That's what's got the power. That's what makes it difficult, because that's hard to expand out, especially if the power is a large number. And the x is fine. Like, the x is like it's okay. We wouldn't care really if the x had a power of 5 on it. It wouldn't really matter, you know. But it's the fact that the binomial, the thing in brackets, has the power of 5, which makes it annoying. When you do the substitution, it flips them round, and we can expand much easier. So what we now need to do is change the limits into limits in terms of u, because you need to change everything to be in terms of u, not just the actual integrand and the dx. You need to turn everything, including the limits, into u's. So what you need to do here is figure out what on earth are the limits. Again, you just use the equation that links x and u together. So if the original limit was between 1 and 5, the limits in terms of u, let me do these in purple, the new limits, I'll call the lower limit ul, will be 3 plus 2 times the original lower limit in terms of x, which was 1. So the lower limit in terms of u, I'll call ul, is going to be 5, because it's 3 plus 2 times 1. Cool. And the upper limit, so u upper, is going to be 3 plus 2 times 5, because 5 was the upper limit for that integral. It was between 1 and 5. And 2 times 5 is 10, plus 3, that's going to give you 13. So that's equal to 13. So all you do is you go back to your original integral here, or the one at least that you're working on, and you rewrite this exactly the same, but your limits are now in terms of u. And so our limits, again, were 5 and 13. So instead of between 1 and 5, it's between 5 and 13. U to the 6 minus 3u to the power of 5 du. Lovely. And then you just do the integration. You just integrate it like you normally would. So this is going to give you 1 over 4, and then I'm going to sort of put some square brackets around this. U to the 6 is going to integrate to 1 over 7 u to the power of 7. 3u to the 5 is going to be 3 over 6. That's going to be minus a half u to the power of 6. That's between 5 and 13. Okay, I'm regretting not having a calculator on me at the moment right now, but we're going to end up with 1 over 7 times 13 to the power of 7 minus a half times 13 to the power of 6. And then we're going to take away from that. Let's see if we have space over here. Yes, we do. We're going to take away a quarter, and then the same thing again. So 1 over 7, but this time it's going to be 5 to the 7 multiplied by 5 to the 7 minus a half multiplied by 5 to the 6. And I'm going to do all of that on a calculator, and I'm going to tell you what the answer is. Okay guys, so it's roughly going to be equal to this number here that I've written down, very large number right there. What is that? 1,636,830, roughly. So a very large number. That'd be the area beneath the curve. Okay. So whenever basically the take home here is, if you're doing a substitution, you need to also change the limits into the new variable that you have chosen, the u. Okay. You need to find what du is in terms of dx, so or dx is in terms of du, and you can replace them. You need to replace everything. Okay. This is the fastest way to do the substitution question. So in the future, we'll look at some more complicated examples. There are lots of examples with quite unconventional, unpredictable substitutions involving trigonometry. So we'll look at all of that in the future, but this is the gist of it. This is the gist of the topic of substitution. Thank you guys so much for watching. I highly appreciate it, and I'll see you in the next video. Cheers.